the PowerPoint that I really wanted you guys to try and read in your book ahead of time, even though this is not on Thursday's test, right? And try and kind of fill in these blanks, because the more you read before I lecture, right, the more it's going to stick in your brain. So the inflammatory process, although your current book puts it, I think, towards the end of that chapter, it's paramount to how the immune system works, right? So I cover it first. It's that important. We start right out with inflammation. So in this process, we really want to focus on the factors that initiate this response. And this is a response. And then what happens? What are the outcomes from this response, right? What happens during inflammation? Swelling, right? We've all experienced this, right? But did you know what was happening at the cellular level? Why it was getting red, why it was getting hot, why it was swelling up, right? There's a reason for it, and then a lot of times, you know, we try to stop it, don't we? Right? But depending on how and why this is happening, you might not want to stop it. So when I broke my crown and my jaw got inflamed because I wasn't chewing right, and I went to the dentist, he said, "Erica, why didn't you take some ibuprofen?" I said, "I only take ibuprofen unless my doctor tells me to." He said, "Well, go home and take some." But I was in so much pain by then, he had to put me on steroids. Steroid dose back, because I was a stupid idiot. But I should have called him sooner, right? And said that I'm really hurting. But yeah, there's times when you need to take it, and really, yeah, you need to have your doctor know. Yeah, it's okay, take it. But if you have an injury or something like that, you need to notify your doctor, right? Because if it progresses, right, it continues on, then there's other steps that need to be taken, right? And you don't want to take anti-inflammatory drugs like ibuprofen without your doctor knowing about it. Some people take it like candy, right? If you're doing that, you're hiding a potentially really big problem, right? And some things can be fixed, right? My jaw is fixed. Which is awesome, you know, when you don't have to, when you can eat and it doesn't hurt, that's pretty awesome. But there's reasons for inflammation, right? There's a purpose to this. So what is the purpose? What are we trying to get to that site where the problem is? Who needs to get there? What cells? We want the white blood cells to get there, right? And sometimes even some of the fluid that the blood that makes up the blood contains proteins that we need to get there, right? So we want to contain the site of damage, right? That's the purpose of inflammation, although it doesn't seem like it sometimes, right? It is actually a containment method. We want to localize the response, right? We only want the white blood cells going to where the problem is. And we want to keep that problem localized. We want to eliminate the invader, right? If something got in, we want to destroy it. Right there at where he got in. And then, of course, we want to restore tissue function, right? And so what turns this system on? When we have invasion, when we have damage. So what are the things we see or feel or experience? You guys named most of these already. Heat, we feel that. We can see swelling, pain, redness, right? So swelling, redness, heat, and pain. And sometimes loss of function, right? Depending on the extent of the inflammation and where it's happening. And that could be in your arm, which can be a pain in the butt, or it could be in your brain and you're terrified you're going to die. This is why location is important. So we will watch now my favorite videos. And they're all on YouTube nowadays, so you don't even have to look in Canvas or whatnot. But I put the links in Canvas, and I keep forgetting to update my PowerPoint to say Canvas instead of Blackboard. So I just remembered that it is important that this darn thing get on the internet. Come on. Aha, yay! It wasn't a joke. It really was on the internet. And I need to log back into Canvas. And go to our class. And under the modules, right, you'll notice there's a lot of stuff for this module, which is module 3, which is down here past case studies. Case studies is a do on your own assignment. Remember I talked about this before I went away. Some of you guys knocked it out. Kudos to you. Others of you still need to get this done. And I talked about that at length before, so I'm not going to say anything more about it. So, animation, videos and animations. Oh, the only one you got to submit is the Listeria one. Yeah. Yeah, so all the rest of them you compile it, and I basically give you the answers if you listen to my recorded lectures and you print out the PowerPoints and you fill them in. Just compile all your notes and everything, and then do Listeria. That's the only one you got to do on your own. It'll give you the answers after you get done, right? And then compile all your notes on all 6 of them, right? Be ready and organized, and then open the test 4 whenever you are ready, and complete it with your notes. And it's not timed, but you can only open it once. So. I don't know, like, I mean, I don't have it in Lockdown Browser, so you should be able to look at it, but I always suggest, like, go ahead and print it out. You had your words open? Okay. Okay. Yeah. So you should be able to apparently look at stuff if you don't want to print. I know some of us don't like to print stuff. So I'm fine with that. I just have a itty bitty little monitor, so I have 2 now though in my office. I'm so excited. I haven't even got to play with them. Okay. So the first one we're going to watch is the leukocyte rolling one. And of course there's an ad. And you guys can't hear anything, huh? Why can't you hear anything? It's not muted. Oh.
At sites of injury, infection,
it's muted on my computer.
Cytokines are released and stimulate endothelial cells that line adjacent blood vessels. The endothelial cells then express surface proteins called selectins. Selectins bind to carbohydrates displayed on the membrane of the leukocytes, causing them to stick to the walls of the blood vessels. This binding interaction is of sufficiently low affinity that the leukocytes can literally roll along the vessel walls in search for points to exit the vessel. There, they adhere tightly and squeeze between endothelial cells without disrupting the vessel walls, then crawl out of the blood vessel into the adjacent connective tissue. Here, leukocyte rolling is observed directly in an anesthetized mouse. The up and down movement of the frame is due to the mouse's breathing. 2 blood vessels are shown. The upper one is an artery with blood flowing from right to left. The lower one is a vein with blood flowing from left to right. Leukocytes only adhere to the surface of veins. They do not crawl out of arteries. Some leukocytes are firmly attached and are in the process of crawling through the vessel walls, whereas others have already left the vessel and are seen in the surrounding connective tissue. When the blood flow is stopped temporarily by gently clamping the vessels, we can appreciate how densely both vessels are filled with red blood cells. Red blood cells do not interact with the vessel walls and move so fast under normal flow that we cannot see them. When the blood flow is restored, some of the leukocytes continue rolling, whereas all non-interacting cells are immediately washed away by the shear.
Oh, they don't even have the credits in this one. Shame on them. But that definitely one of my all-time favorite. I have no idea how they did that. It's pretty freaking awesome, though. Yeah.
To visualize lymphocytes.
No, I mean, I think it's, I want to pause that. I don't even know if that's microscopic. I mean, how would you do that? I have no idea. I've not investigated. It's pretty impressive, though. So who's in anatomy and physiology 2? No, not there yet. Or been there? Been there. Okay. So little anatomy quiz, because they said they don't crawl out of arteries. Why not? They're what? Right, arteries that go away from the heart. So what does that mean about pressure? Too much pressure, going too fast, right? Superhighway, way too freaking fast, right? You cannot exit the highway going 90 miles an hour, although some idiots try. Not a good idea. Right? That's problem 1, too much pressure, going too fast, right? What's problem 2? Artery. How many layers? They have a muscle layer, don't they? Yeah. Too many layers to try to get through, right? Veins are much thinner, right? Capillary is the thinnest. Right? And so less pressure, moving less, not as fast, right? And less to travel through to get out into the tissue. So that's the why. They come from there. Okay, so this next one shows you again, remember, the whole thing started out, do you guys remember, right? Something got injured. So in this case, they took a zebrafish, and this is definitely probably under the microscope. So they're little tiny fish, and they pierced it, right? So they purposely wounded it, right, and filmed it. And this actually, this film has been sped up. It doesn't happen as fast as you see it in the film. And I think they even tell you that in this. So the first step, how did the cells know to go to where the injury was? Do you guys remember what they said? Cytokines, right? So I always tell my students, think of cytokines as the hormones of the immune system, right? Hormones tell the endocrine and basically your whole body what to do, right? Cytokines communicate with your immune system. These are the chemical message of your immune system. And I kid you not, it's a huge ass book of all the ones we know and all the interactions, and it gets bigger each day. You think hormones are bad? Don't even get started on cytokines, y'all. If you seriously, like, you think, nah. Cytokines have got hormones beat, hands down. There's way more of them. There's way more interactions, way more cells and things going on, and we still don't understand the whole web of communication that happens in the immune system. I mean, we're just scratching the surface as far as research goes, and we're literally just skipping over the surface in this class of immunology, right? Did you have something, Kat? Or Ashley? Okay, you got it. Yeah, so they're the chemical messages, right? So it's all chemical for our cells. That's how they communicate, right? This is how they send signals to each other. So same signaling thing as what hormones do, except just a different system and way more complicated. So there's a signal, right? These cells right now are literally releasing cytokines going, ow, ow, help, help, right? And their friends come rushing to their aid, okay? And this is a specific signal, right? So these guys are screaming, and then here come their friends.
Anesthetized, and its fin pierced with a needle to introduce a small wound. A vein is seen at the bottom of the frame. Because the fin is very thin and transparent, we can watch directly as lymphocytes crawl out of the blood vessel and migrate towards the wound. They are attracted there by chemicals released from damaged cells, invading bacteria, and other lymphocytes. In a zoomed-out view, we can appreciate that lymphocyte invasion is restricted to the wounded area. The static cells that are dispersed in the connective tissue are fibroblasts.
Those are the ones that make
In these
connective
movies,
tissue.
60 minutes of real time are compressed into 15 seconds.
So that was an hour, right, that we saw in 15 seconds. See, there's the credit. London. Thank you, London. You're awesome. It is, right? And I find, too, like, I mean, I'm sure these things didn't exist. I've been showing these videos for like 10 years now. I love them. Because, right, you really can, when you see it, you can really be like, wow, you know, I bet chemistry teachers wish they could show videos of molecules. But now, I mean, like, they're doing all these 3D modelings and stuff nowadays. I mean, you no longer have to try and conceptualize this or build little models. You can watch it on the computer. It's insane. But here, we just watched it, like, in a real organism. What happens all the time in our bodies, right? When we get damaged, when we get invaded, right? Our white blood cells just go running there, right, to take care of the problem. So this is an animation by the textbook. So they're going to go into a little bit more detail, but it doesn't have the odd factor of like the real thing, right? But it's still good. It's a lot of information here, and they go into a little bit more detail in some areas, but we're not going to focus too much on some of the details, but I'll tell you the ones that are important. But this is a good animation. I mean, they did a good job.
The inflammatory response is an important non-specific defense against tissue damage. It begins when injured tissue cells release chemical signals that activate the endothelial cells of nearby capillaries. Within the capillaries, adhesion molecules called selectins are displayed on the activated endothelial cells. These adhesion molecules attract neutrophils, slow them down, and cause the neutrophils to roll along the endothelium. As the neutrophils roll along the endothelium, they encounter chemicals that activate integrins, which are adhesion receptors on their surfaces. These integrins then tightly attach to adhesion receptor molecules on the endothelial cells. This causes the neutrophils to stick to the endothelium and stop rolling. This accumulation of neutrophils along the walls of a capillary is referred to as margination. The inflammatory mediators released by the injured tissue bring about changes in the environment that cause mast cells to degranulate and release histamine. Histamine causes vasodilation and an opening of the junctions between the endothelial cells, allowing fluid and leukocytes to leave the capillary and enter the infected tissue. The neutrophils now undergo dramatic changes in shape and squeeze through the endothelial wall into the interstitial tissue fluid. This process is called extravasation. The neutrophils, followed by other types of phagocytes, are attracted to the damaged site by chemotactic substances released by bacteria and tissue breakdown products. They ingest and destroy invading bacteria.
So I like this one, you know, I mean, a little bit more detail, like I said, you know, like they're literally, you see the phagocytosis that's happening. They're being specific as to the first type of white blood cells that tend to come on the scene, which are the neutrophils, right? So they're being a little bit more specific here. They're bringing to light some of these other white blood cells that are commonly found in your tissues. They release a substance a lot of us are pretty familiar with, right? Histamine. Because there's sometimes other things that will cause these cells to degranulate, especially people who have allergy, right? We have special antibodies that interact with mast cells and basophils and cause them to degranulate, release that histamine, which causes the vasodilation, right? So we get inflammation, say, in your nose because of an allergen you inhaled, not something that's actually going to hurt you, but your immune system is recognizing as foreign and potentially dangerous. And it's doing its normal response, right? It's inflaming, except you don't need to inflame over ragweed pollen, right? So histamine, what do we usually take to combat histamine? Antihistamine. What people don't realize, though, is that after the histamine's already been released, you can't do anything about it. You need to take an antihistamine before you're exposed. It's actually preventative medicine, and most people don't understand that as far as allergy goes. You should take it before you go to your friend's house who has a cat, if you're allergic. You should take it every day if you're like me and you're allergic to just about everything outside in the air you breathe before you leave your house. Right? You can take it after. It's going to help you with any additional exposure, but it's not going to fix the problem of the first exposure you had and the inflammation you had. And depending on the degree of that, that's why a lot of those antihistamines also come with what? To get rid of the inflammation response or help clear it up. What does the D stand for? Zyrtec D and Claritin D and Allegra D. Decongestants. Contains a decongestant. 2 different drugs. One's a allergy medicine to help you with future exposures, and the decongestant is to help you with the exposure you had without medication or without sufficient medication in your body. Make sense? Because when that gets released, it can't bind to the receptors if the antihistamine's already there. The antihistamine is out-competing the histamine receptors. So it doesn't like digest the histamine or anything like that. It actually competes with the histamine for what the histamine binds to and the reaction that it causes. So what caused the release of inflammatory mediators? What do we got here? Yeah, we've got damaged, right? So the damaged tissue, right? And then if somebody also got in, breached the barrier, the invading microbes themselves, right? We know this too, right? Like, you know, when they grow in your food sometimes, right? You're like, ooh, that doesn't smell good, right? Right? Because microbes, especially if you're taking lab, you know this when I open the incubator, right? They don't usually smell good to us, right? They produce waste, right? That evolutionary-wise probably makes sense that we don't think it smells good, right? So we won't eat it and die. So they release substances that our body recognizes as foreign, right? So they can recognize different components and different things about them, their structure even, that our body has receptors for to detect, oh no, this is bad news. This is an invading microbe. So how do the white blood cells get to the area? They ride the superhighway, right? What's the superhighway? Our blood, right? Our blood vessels, right? So we get increased blood flow to that area, right? Because that's how they're going to get there, so we got to make sure the blood is going there. So what do you see and feel because you have increased blood flow? The redness, right? The heat, the swelling, which also leads to the pain, right? So the redness is just increased blood flow. But why is it hot? Blood is hot. Blood is hot, y'all. Blood is what absorbs the heat from your metabolism, and it distributes it throughout your body. This is why when you start working out, especially if you're fair-skinned like myself, you get what? Red, because you get increased blood flow to your skin. You're like, why my skin? My muscles are the ones that, well, it goes there too, but it's going to the skin because your muscles are producing so much heat that it's going to go to your skin so that you can start sweating and you get convection and you get rid of that heat. So how do you tell the difference between Asian and African elephants? The size of their ears. Guess who's got the big ears? The African elephants. Which one do we have in our zoo? They got little ears. They're Asian elephants. If you look, right, they have the little ears. African elephants, huge ears, right? Why? So they can pump the blood into that very thin ear, and that's also why you'll see them fanning their ears, right? They're always flopping their ears, right, when you see them in those videos of Africa. They're trying to cool off, man. It's freaking hot. It's hot, right? So same thing for us, right? But in this case, again, blood is always going to be hot. And if you've got that increased blood flow, it's going to get hot because blood is hot. metabolism, when we break down sugars or amino acids or whatever it is we need to for energy, it produces a lot of heat. So then they make gaps, right? And, you know, make a gap, the fluid's going to come out, right? You spring a leak in the hose and it's going everywhere. Okay, so the fluid is going to leak out, which sometimes that's a good thing too, because there are things in that fluid that are protective, like antibodies, right? And fibrin for making a clot, right? Or help sealing up if there's a major damage to the blood vessel itself or to the tissue. We can utilize some of those proteins that's in that fluid. But it's going to, again, especially with your skin, thank goodness it's going to stretch, right? And you're going to get swollen. And it's going to push up against the pressure receptors. And that's why you go, ow. That's why it's painful. Because that fluid is pushing up against those receptors that are in your skin. Does that make sense? So what proteins, right, are coming out? I just named a whole bunch of them. Antibodies, the clotting proteins, right? Also transferrin. Trans means what? To travel, right? Ferrin is referring to what? Iron. Iron isn't very, remember ferrous is another name for iron. Isn't very soluble in water, so we actually have transferrin in our blood to help transport it. But it's also going to help us absorb any iron from the cells that died and keep it away from microbes. Because remember, they need it too. They need it so badly, some of them have adapted to producing enzymes that will lyse our red blood cells to get to it. Complement is a series of proteins that we're going to talk about, right, that have very protective components to them. So we'll table them for now, but know they're coming back around. Antibodies, as I said, that can specifically bind to specific pathogens. They're proteins, right? They're very protective, very helpful. They're a very specific wanted poster on the bad guys. And then the clotting factors, right? And they can help wall off the area like we wall off crime scenes with tape. Which New Orleans must, own stock in that stuff. So how specifically do they get out of the blood vessels, though? Why do we see this rolling interaction here? There were signals sent, right, specifically to the endothelial cells, and what do those endothelial cells do? They stay the same. They're just like, oh, nothing's wrong here. It's all good. Nobody's over there. Don't look. What do? Yeah, but how do they know that this is the spot to exit? They adhere to these blood vessel, right? Because they express molecules. It doesn't matter the name of them, right? But they express molecules that those guys are going to specifically attach to, and generally refer to these as adhesion molecules, right? Because they literally help them adhere to the blood vessel walls. That's why they're interacting. That's why they're leaving here, right? And this squeezing or oozing effect is sometimes referred to as diapedesis. So pro-inflammatory cytokines is what starts it, right? So these are ones that start this reaction. And we get these adhesion molecules expressed. That now these guys can grab onto the adhesion molecules, right? And then they're going to squeeze through, right, that process referred to as diapedesis. Means to ooze. So again, remember, this doesn't happen everywhere in our body. This happens when they're called up, right? And we got to facilitate that movement. It's like the air traffic control guys. Right? Got to get us where we need to go. So anybody remember what was the white blood cell that they said in the animation we just watched that comes on first? Neutrophils. Yep, neutrophils. And these are phagocytic, because as you saw, they literally will gobble up. And we're going to look into the specifics of that tonight as well, of that process of phagocytosis. Right. The next ones, and you guys got them? Who tends to be next? Next is your macrophages, which when you're looking at blood under the microscope, we refer to these guys as monocytes when you're in your blood. But they differentiate into macrophages in your tissues. And macro meaning big, right? Phage, eating. So these are your big eaters. They're going to eat up a lot of microbes as well as debris from dead cells, tissue debris. Then last would be your lymphocytes. And these are part of our adaptive immune response. So we're going to talk about their specificity, the different types of them and what they do when we get to your adaptive immune response. I always caution students not to use the term leukocyte because it sounds an awful lot like lymphocyte. And they commonly interchange these two. Leukocyte is a general term for all white blood cells. So I always say, just stick to white blood cell. And I guess I was a nice AMP2 lab teacher because I let my students write white blood cell. You didn't have to write leukocyte. And the reason why I say that's nice is it's a whole lot easier to spell, isn't it? Also, I never wanted them to mix it up between that and lymphocytes, which is a subgroup of white blood cells, of leukocytes. Right? So you have white blood cells, but within white blood cells you have bunches of other groups, right? You have neutrophils and macrophages and lymphocytes and granulocytes, which neutrophils fall under. And even within lymphocytes, you have B cells and T cells and natural killer cells, right? So there's all this organization we're going to talk about. But as I said, unfortunately, people confuse lymphocytes and leukocytes sometimes, and that's a big no-no. They are not synonymous terms. Make sense? All right. So you learned, all right, no one's taken AMP? 2? 1. Aubrey. So, never let monkeys eat bananas. It's a saying that most of us know that study white blood cells. That's the order of most abundant to least abundant of the 5 different classes of white blood cells that you categorize in blood when you're looking at a blood smear under the microscope. So never for neutrophils. Those are your most abundant. As you can see, they're the first on the scene, right? Those are the most abundant under normal conditions. These levels will change when you have some type of infection in response to that infection. So what do you think? Never let, what's the L stand for? The lymphocytes. Monkeys, M, monocytes, right, which turn into macrophages in your tissues, right? Never let monkeys eat eosinophils, which is a granulocyte. Bananas is the last one. Basophils, which are your least abundant of the granulocytes. Very rare. I always said if you actually see it confirmed one under the microscope, you'd see me do a happy dance. Because they're really rare under normal conditions. I should put that, I have a worksheet for that. I should add it to my PowerPoint for you guys. So what do the white blood cells do? What are they doing here in this picture? Yeah, they're doing phagocytosis. They literally engulf and destroy the invaders. So both neutrophils and macrophages do that, do phagocytosis. So they're going to destroy and remove invaders. Right? They're going to ingest dead cells and debris as well. Mostly the macrophages. What is in pus? What's pus? When we have pus? Dead neutrophils, right? Is pus a good sign? No, never. Never. Pus is not good. If the neutrophils are dead, are they eating the bad guys? No. Pus is never good. It's tissue debris. It's the pathogens too, because think about it, right? This is why, like, when people have pus, most people go, ooh. Other than the fact that it looks gross, you really want to go, ooh, and you don't want to touch someone else's pus, right? Because it means that the immune system's not taking care of the problem, right? It's overwhelmed. The cells are dying, right? The bad guys are winning. Pus is bad, always bad. If you have pus, you have infection. You need to go to the doctor. Ooh, glad we cleared that up. Okay, so this is a great schematic, right? Kind of goes through all the different steps, right? So say we get a splinter, say some bad guys get in along with that splinter. You have resident macrophages that are always in your tissues and your skin and all your major organs. And we talk about them later. When scientists were first discovering them, they actually gave them other names. And then come to find out, it's like, oh, it's just a macrophage that lives in your liver. So a Kupffer cell, right, is just a macrophage that calls the liver home. Right? So these things, when they're born from your bone marrow, they disseminate throughout your entire body. And they take up residency to be resident guard dogs always on duty. So the minute those bad guys get in, they're going to start eating right away. But are there enough of them to take care of the problem usually? No, they got to call in reinforcements, right? So they're going to, especially they have receptors for pathogens. If they recognize and start engulfing a bunch, they release cytokines. The cells that were damaged release cytokines. You know, you may even have mast cells releasing histamine nearby. I mean, there's a whole lot of screaming going on because there's a whole lot of problem here. So what's going to happen, right? Those signals are going to be transferred to the blood vessels. The white blood cells are going to come on scene, right? The blood flow is going to increase to that area because of all that screaming, all those cytokines being released. And so the main guys that are going to get there are neutrophils. These guys are really powerful killers. And they'll even kill themselves to try and kill the bad guys. I call them our suicide bombers because they'll do stuff like that. And then more macrophages will come, right? They're called monocytes in your blood, but they're going to differentiate into macrophages. So they've been recruited. They weren't the ones living there, right? They're the recruits. And then remember, again, it's, you know, they've got to actually interact and know exactly where they're going. So to review, what's the purpose? Localize, right? So contain that site of damage. We want to let the bad guys get in and run around? No, 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 right? We're going to localize them and we're going to eliminate them. And then, of course, we got to clean up the mess. Right? So we're going to restore tissue function. What are the cardinal signs that let us know that a response like this is happening? What do we see, feel? Right? Swelling, heat, redness, pain, and maybe even loss of function. You guys ready for a break?